Welcome to this presentation of autoencoder-based joint communication and sensing of multiple targets. This was a joint work with Schmalen and it was presented in the context of the WSA-SCC conference 2023. To start, I'd like to talk why combining communication and sensing is useful. So firstly, it enables us to use more frequency bands for communications or for sensing, so we can use cross usage or use it for both. Therefore, we improve the spectral efficiency. We can also improve the energy efficiency just because we don't need to send out more energy if our communication signal is already the one used for sensing. And then we also want to use synergies. This is a topic of sensing-aided communication or communication-aided sensing, where one profits from the other functionalities. Therefore, concerning our 6G network, efficient sensing algorithms that are compatible with our communications or with our high-speed communication are needed. Here in the graphic, you see a monostatic base station here that communicates here with this phone. But at the same time, some energy is sent here towards these passive targets. So these are not active senders, but there are a lot of metal. They reflect the signal. And when we receive these reflections at the base station, we can learn something about our environment. Secondly, the question is often asked why we use machine learning methods for this. So usually we use some kind of model-based algorithms, but most of these models have some problems or some deficiencies, especially at very high carrier frequencies. Or there are some effects that we just cannot model properly, and therefore these data-driven algorithms are really well suited. There is some existing work using this in a monostatic sense, this joint communication and sensing, where we also use this split beam that is shown on the right, where we know that our sensing targets are, for example, in this area, and our communication targets is expected in this area. So we form these two beams and can then do both at the same time. The existing work is only focusing on detection of a single object. And now with this presentation and with the paper, we extended this to multiple target case. This is our system model. At the beginning here, this is the communication system. We have our encoder, which takes these symbols M, and encodes them to some complex representation. Then on the bottom, we have a beamformer that takes basically the minimum and maximum angle of our targets and of our receiver, and then basically applies here a precoding. Both are multiplied, and for the communication path then put through a Rayleigh channel. And then our communication receiver receives the received signal, and we can estimate or we can decide what our communication symbols were. We assume that we already have a perfect channel state estimate for this. So the channel state information kappa is known here. Then on the top we have our sensing path, which is for the radar channel here we use the swirling 1 model to model the different targets, and then we feed this into two different parts, one performing the target detection and one performing the angle estimation of the target that are detected. All these blocks that are marked in blue were implemented as neural networks, so we can have this nice autoencoder approach by optimizing the transmitter and the receiver jointly. Go. Okay. So, as mentioned, we have this neural network structure, and we use for each neural network 3 hidden layers, and we use an ELO activation function also for all hidden layers. Then our encoder has a maximum layer width of 2m, while m is the number of communication symbols. Same as the decoder. The encoder needs some mean power normalization at the output so that the energy that we transmit doesn't diverge to infinity. Then our beamformer has a maximum layer width of 2k, while k is the number of antennas. And there we also need to apply some kind of power normalization. Then the decoder has the same layer width as the encoder, and we have a softmax output layer so that we have basically a soft probability that a certain symbol was sent. The target detection has again a maximum layer width of 2k with a sigmoid output, which basically tells us whether there is a target or not. It's kind of similar, just the end to the decode to the softmax here, the approach, but our target detection is encoded quite a little bit differently, but we'll get into that later. And then lastly, the target angle estimation also has a maximum layer width of 2k, and we have a tangent hyperbolicus output layer, so because we just want some angle estimates. Then, we simulated here with the uniform linear array with 16 antennas in the transmitter and in the sensing receiver, which we assume to be the same object or the same device. And then we perform 2 types of simulations. First, the single target simulations with only 4 communication symbols, 1 target, and here quite low sensing SNR. And then we also performed the multiple target simulations with double the amount of communication symbols, 3 targets, but also quite a lot higher sensing SNR. This was just needed so that we can get rid of the interference that the different targets pose on each other. So then we have now designed the networks. Now comes the other hard part. We need to define a loss function so that our neural network optimization actually achieves some gain. So for the communication, we use this well-known approach using a bitwise mutual information as an evaluation measure, and therefore using the binary cross-entropy loss. For the angle estimation, we evaluate it based on the root mean squared error, therefore we can have a mean squared error loss. And for the target detection, we also use the binary cross-entropy loss, and we evaluate based on the detection and false alarm rate. So here we evaluate this based on the basically false right detection and false alarm probabilities. And yes, we need this BCE loss, again, because of our encoding that I'll show later. We saw that our results improve if we split our training into 3 different parts, and in each different part we adapt the loss function a bit. Meaning that here in the first part we only train the angle estimation and the communication. In the second part we only do communication and detection, and then in the third part we have all 3. Then I have here these weighing factors. We just swap them and then set them to reasonable values. So this is why we have here 0.9 and then 20 for the angle. Here, now we get to our first problem concerning the evaluation. We say that we now go with multiple targets, which means that our angle recognition is here based on sets, so on some collection of angles, which is not ordered, and not on vectors. This means there is a certain kind of ambiguity that we need to resolve also during training in order to get a useful gradient, and also for the performance validation later. And here at the bottom you see a little example here why this happens. So at our neural network output we get the same amount of angles than we have output neurons. And now the first step that we do is that we select the first couple of these angles according to how many targets were actually detected. So here we have 2 detected targets, so we select the first 2 of this object here. And then we also have these 2 validation angles, but the order in how we should evaluate this mean squared error here is ambiguous. So either this is our error or this. And we know it should be the minimum, but yeah, we looked at certain different ways how we can handle this problem. 2 of these methods rely on sorting. So we have one that is this sort input, where we take our valid angles and we sort the valid angles. And then here we just take the raw neural network output, which should incentivize the neural network to also give the results in an ordered manner, also so already sorted. Then we have the sort all approach, so as a comparison whether this actually works or not. So we sort the neural network outputs, the valid angle outputs, and then do our mean squared error. And lastly, we have basically an optimal version, which is this permuting, where we take our valid angles and then we also look at our neural network output, and then we calculate all permutations of our mean squared error and kind of just choose the lowest. Complexity-wise, of course, these methods perform quite different. For a target number of 3, this might not make a big difference, but for other similar problems, this might really enable us to work on these sets, and not to have to do this permuting approach. Now we come to the results. Here at the beginning you can already see the none curve, which is just there to show us that some kind of approach to handle these sets is needed. We can see we get an error which is like not that great, and now we have these 3 curves where we have our different set methods, I'd say. As expected, the permutation performs best, but then the sorting approach is almost the same. So for higher complexity problems, I'd encourage to just try this sorting approach out. And then the sort input, we can see that it gets rid of quite a bit of errors, but not fully. So I'd say depending on how on the problem at hand and depending on how much complexity we can spend on being here as exact as possible, all these approaches might be valid. And this is our Esprit methods. There we also do this, we kind of also do a permutation afterwards. As you can see, for these very low number of samples where we just trained for 1 sample, our Esprit is much worse than our neural networks. But if it increases, so if our oversampling factor increases, the Esprit method quickly overcomes our trained methods. Here the spike is just caused by us having implemented a single snapshot approach or a single snapshot variant of Esprit for the oversampling factor of 1, but not for 2. So this is why we get this peak. So we have like an optimized version for 1 here, and then the raw usual Esprit method. So now we get to the next problem, which is that we want to set a targeted false alarm rate for our system. So we don't want to just say, well, we know that we detect in 80% of the cases, but in 20% of the cases we have a false alarm. We want to fix one of these values and then train to a value as good as we can. And this is where our encoding approach that I already mentioned comes into play, which we call the counting encoding. I guess I'll just explain it here on this example. It's quite simple. So if we have a maximum number of targets, which is 3, and we know that we have 2 targets, then our vector, our encoding vector is just, we have 2 1s in our vector, and then we just fill it with zeros. So we just put as many 1s as we have targets here at the beginning of this vector. The rest will be zeros. And this is what actually enables us to really nicely set this false alarm rate. As a comparison metric, we use here some one-hot encoding. And we interpret here encoding-wise this as a classification problem, meaning that we classify into having 1 target, 2 targets, 3 targets, 0 targets. Which means that we have here, with the same example, having maximum of 3 targets and detecting 2 targets, we have here this vector which encodes this, meaning there would be a 1 here if we had 0 targets, a 1 here if we had 1 target. Since we have 2 targets, we have here the 1, and for 3 targets there's the 1. As you can already see, our encoding vector gets shorter with our method, and we will see which other effects this has. And one big difference here is that for the counting encoding we can just smartly modify our output logics to really fix our false alarm rate. And for one-hot encoding, the only way we had for fixing this was that we modify the output probabilities, which means that we cannot really get to the raw data. So, and this is the results of this simulation. As you can see, our proposed counting encoding detects a little bit worse during training, so this is a during training curve. And the one-hot is a little bit better here. But I mean, I'm already showing this to you. What really is interesting for us is our false alarm rate. And this really nicely targets or keeps at the targeted value of 10 to the power of -2 for our counting encoding. And for our one-hot encoding, first at the beginning we get this really large peak. So, which means that it's, even if we get it under control, it's not controlled as tightly as with the other approach. And we also oscillate at like a higher level, which just gives us to think that, well, the way we modify this is not 100% effective, and the loss function seems to push it up again. So, I'm already coming to the conclusion and to the outlook of our work here. We built this joint communication and sensing system using the autoencoder approach with our machine learning methods. Then we saw that we can perform the simultaneous communication, target detection and angle estimation. We saw that the counting encoding enables the detection of multiple targets, and our set methods that we developed really got rid of the problem of our angle ambiguity. My take-home message for you would be that the method that we showed could outperform our Esprit benchmarks for a small number of measurements. This novel counting encoding approach really enabled us to have this fixed false alarm rate even in a trained system. And the set methods are suitable, and the choice should always just be depend on the trade-off between our estimation precision and the algorithm complexity. Lastly, if you want to play a little bit around with the code, you can find it at GitHub.